Hello everyone, welcome to another video in a series of videos about statistics. Today we are going to build on top of the previous video that we did on linear regression analysis. In the last video we discussed the theory behind linear regression and the basic principles of linear regression. And today we are going to apply that theory in a setting where we're going to use the software SPSS, and I'm going to show you how you can run a linear regression and interpret its results, as well as checking the necessary assumptions that you take when you do linear regression. And to demonstrate that, we're going to use a very simple data set, which is based on a real data set, but I'm just using the variables necessary to show you how linear regression works. And we are actually going to look at the same relationship that we looked at in the previous video, namely the relationship between BMI and systolic blood pressure. But in this case, it will be based on real data. So it will look a lot more realistic, and we won't be seeing the big proportions of variance explained that we saw in the previous video, where we only had 5 observations. All right, without further ado, let's get right into it. So the first thing that I would recommend you always do doing any type of analysis really is to describe your data both numerically and visually. And in this case, we're going to do the latter. And since we have two variables that are both quantitative continuous scale, we are going to use the appropriate technique for that. We're going to use a scatter plot. Remember that we also use the scatter plot to describe how linear regression really works. So this is the most appropriate technique to use in this case. So we can do that by going to graphs, legacy dialogues, scatter/dot. And we're going to choose simple scatter. And there are two things in this new pop-up that we need to define. We need to define the dependent and the independent variable, or more specifically, the variable on the y-axis and the variable on the x-axis. And more often than not, we'll put the dependent variable on the y-axis. That's the way we did it last time. And we put the independent variable, BMI in this case, on the x-axis. So we're going to follow that same structure over here. And when that's done, we can write it away to the syntax, go to our syntax menu, and run that piece of code. Now, this will be the result, and there is a couple of things that we can note. But one of the most striking things is that all of the dots in our scatter plot seem to be clustered on the bottom of the graph, which is kind of strange because there is a lot of space in this graph to use. But the reason that these points are so clustered is because there is one dot all the way at the top at a value for systolic blood pressure of 1,000. And that is a bit strange, of course, because a person with a systolic blood pressure of 1,000 is just not really possible. So this seems to be an impossible outlier, and it's biasing our results greatly. So we'll need to do something with that outlier to make our graph more representative of what it really should look like. Now, in this case, it is actually a missing value because I can tell you that this is coded as being 999, which are generally a way of coding your missing values. But in order for SPSS to know that that is a missing value, we have to make sure that it treats it as one. And to do so, we'll have to go back to our variable view. We go to the variable systolic blood pressure, and under the column missing, we have to define the discrete value that SPSS needs to regard as a missing value, which in our case is going to be 999. Press OK, and it will appear in the column as appropriate. Now we can run the syntax for our scatter plot again and see what happens next. And in that case, we'll get something that looks a lot more reliable, something that actually looks correct. There are still some outliers, of course, but nothing out of the extreme ordinary, like 999, for example. And so this is a great way of looking at our data. Now, there are a couple of other things that you can look at when you have a scatter plot, namely, you can look at some of the assumptions. Sometimes it's a bit difficult to really grasp the assumptions like linearity and homogeneity of variances, but you can get a general feel of those two, assumptions. For instance, let's look at homogeneity of variances, for instance. Remember that homogeneity of variances meant that along the regression line, which we haven't drawn here yet, the variance in the dependent variable, blood pressure, has to be about equal across the entire regression line. So for different values of x, in this case BMI, the variance in y, blood pressure, has to be roughly the same. And in this case, it doesn't seem to deviate from that as strongly. Remember that if it were to be the case that there was no homogeneity of variances, you would get these cone-like shapes. And in this case, there is no real trace of that. Now, another thing that you could sometimes grasp from using graphs, scatter plots, is linearity. That's a bit trickier here because it seems just like a random ball of dots. But one way to kind of grasp it is to add a regression line to the graph, which is easily done by double-clicking on the graph. A new screen will pop up, and you can click on Add a fit line at the total. You get another screen, and you can just close this because we have already selected linear. We want a straight line, and we can close this off as well, and it will appear newly added to your graph. Now, we actually, in the process of adding this line, we already behind the screen, or behind this whole process, we actually fit a regression line using linear regression, because this line is actually fitted with the ordinarily least squares method, the one that we introduced to last time in the last video. And you can even see that there is an r² value popping up, but we'll get into that in a second. You can also see that the regression equation is added to the fit line, but to illustrate is that there seems to be somewhat of a linear relationship here. So that is one way of getting a feel for some of the assumptions. Now, obviously, we might need other ways of testing or checking whether these assumptions hold, but scatter plots can at least give you some kind of general idea and whether or not they deviate strongly from those assumptions that are necessary. Okay, let's get down to business. Now we're actually going to run a linear regression in SPSS, and we're going to do that by going to Analyze, Regression, obviously, Linear, and we'll get a new screen. Now in this screen, we need to define a couple of things, namely the dependent variable. And remember, we were using systolic blood pressure as our dependent variable. We want to try and explain systolic blood pressure using body mass index. And then obviously we need to add body mass index to the independent variables. Now, with linear regression, we can actually use multiple independent variables, but in this case, we only have one, meaning that it's a univariate model, just one explanatory variable and one outcome variable. Now, there's a couple of things that you can add to your output. Namely, we are going to go to statistics because in our regression output, I want to have confidence intervals. You can actually also give the level of confidence, but generally in the health and life sciences, we're using 95%. And that will be that. So we can press continue. And additionally, I want to go to plots. And I want both a histogram and a normal probability plot for the standardized residuals. So with that, we're going to check our assumption of normality of the residuals. Remember, we had to check that as well. Well, we can actually only do that by actually running a regression because we need to run the regression in order to get the residuals. So we'll go ahead and do that. And that will be it. We'll paste away the syntax and we will run it so that we can actually look at what we'll get. All right, so we'll get a whole bunch of output. So let's just go through this step by step. We'll not go over everything, but most of it will be covered. So the first table that we'll see is the model summary. Now the model summary has one thing that we discussed in the previous video, which is the R². Remember, that was the proportion of variance that was explained by adding the regression line. So in this case, it's the proportion of variance explained in systolic blood pressure after including BMI in our model. And as you can see, in contrast to our previous video, this is only 2.2%, 0.022, 2.2%. That is not a whole lot, not as much as 70% that we saw in the last model. And that is to be expected because systolic blood pressure is probably dependent on a lot of different things, not just BMI. Now, there are a couple of other things in this table as well, such as the R, not the R squared, but the R. And in the case of a univariate model, the R is the correlation coefficient. Now, I won't go too deeply into that, but in this case, our correlation, the correlation between BMI and systolic blood pressure, is roughly 0.148, which is not very strong, but it's a standardized measure of a linear relationship. Then next to the R square is the adjusted R square, and the adjusted R square is basically the same thing as an R square, but it corrects for multiple independent variables. Which is something that we're not going to use in this video because we're just looking at a univariate model. So in that case, we'll just use the regular R square. And then finally, there is the standard error of the estimate, which is actually the standard deviation around the regression line. And it's also something we won't cover in this video, but it's used to construct confidence intervals around the regression line and make predictions. In the second table, the ANOVA table, the analysis of variance, which that is for short, shows us the things that we saw earlier in the previous video as well. We see sums of squares. Remember that we use those sums of squares to determine how much variance was explained and how much variance was residual variance. So in this case, there are three sums of squares. We have the regression sum of square. That's the proportion of sums of squares of variance explained by the regression line that we've added using BMI. We have the residual sum of squares. That was the total square distances from each observation to the newly drawn regression line. And we have the total sum of squares, which is the total variance, the total sum square distances in systolic blood pressure without BMI. Now, remember that we could derive the R squared from these two by taking the regression sum of squares and divide it by the total sum of squares. That way we got the R squared, namely the proportion that was explained by the regression line. Now, we didn't cover this in the last video, but we can also do some statistical testing with the sums of squares. Namely, we can divide the sums of squares by their respective degrees of freedom, and that results in the so-called mean squares. And we can also divide the mean squares by each other, and we will be left with the F statistics, or the F ratio. Now, the F ratio follows, not surprisingly, a F distribution, and given the value under the null hypothesis, we can calculate the probability of observing this particular F statistic given that the null hypothesis is true. And in this case, we can see that our p-value for that is 0.019, which is statistically significant at the 0.05 alpha level. So what that means is that we can discard the null hypothesis that there is no relationship between BMI and systolic blood pressure and conclude that there is, in fact, a relationship between BMI and systolic blood pressure. So that is one way of determining whether or not there is a relationship. But that just gives us information on, is there a relationship? And generally speaking, we are also interested in looking at what is the relationship. So what does the relationship between BMI and systolic blood pressure look like? And that is the part that we can see in the next table, namely the regression equation. And that is this table right here, the coefficients table. And we can see one thing that we saw in the previous video as well, the constant. So remember that was the intercept. So in this case, it's called the constant. It's the same thing. And that was the value for Y, the estimated value for Y, systolic blood pressure, when all of the variables are 0. So in this case, when body mass index is 0. Now, of course, that's a bit strange, once again, because people with a BMI of 0 do not exist. But it's a starting point for the regression equation that we just need to have. It's a part of the regression equation. Additionally, we see a coefficient for BMI, for body mass index, and that's our regression coefficient, our B1. It's the estimated difference in systolic blood pressure, in this case, our dependent variable, for each unit increase in the independent variable, BMI. So in our case, the estimated blood pressure increases with 0.974 for each unit of BMI that increases. So because it's a linear function, that is the same across all units of BMI. So it's the same as, say, an increase from 21 to 22 as it is an increase of 30 to 31. And with that output, we also get the standard error of the regression coefficient. So that helps us in statistically testing the regression coefficient. And we can do that easily by taking the regression coefficient divided by the standard error, and we will be left with a t-statistic. And of course, with the t-statistic, we can calculate the probability of observing that t-statistic. And in this case, we get the same conclusion that we saw with the f-statistics earlier. Namely, it's a significance level of 0.019. It's just a different approximation, but we draw the same conclusion from that. We can also see the confidence interval around our regression coefficient. So with that, we can say that we are 95% confident that the real association or the real regression coefficient in the population lies between the limits that are given. So 0.159 to 1.790. So that is usually the central piece that we use in regression analysis. So this table is often the thing that you'll be looking at and interpreting. Now let's move on to the last bit that we are getting, the things that we asked for, namely the histogram and the normality plot for the residuals, the standardized residuals. So remember what we did when we were using, when we were doing linear regression. What we were doing was looking at how much residual variance there is left after fitting the regression line. So when we go back up to the scatter plot, you can see that after fitting the line, some of the variance had been explained. But as you can see, there is still a lot of spread around that line. And how much there is left will be our residual variance. And each observation has a certain value that is their residual. And all of those residuals together need to be approximately normally distributed. And that's what happens in these plots. So you can look at it either from a histogram point of view or a PP plot point of view. Both are same ways of judging whether or not this fits a normal distribution. And in this case, it does so quite nicely, actually. There is nothing that looks very striking, plus we have a fairly large sample size. That means that we could possibly apply the central limit theorem. The same thing happens here in the normality PP plot. The more nicely these dots are aligned with the black reference line, the more normally distributed it is. And in this case, it deviates somewhat, but of course that is to be expected due to some random variation. All right. One thing before we stop with this video is that to take a little bit of a closer look at the assumption of linearity, because we talked about this in the scatter plot, but as you can see, it's still somewhat difficult to really determine whether this fits a linear function. There is not really any hint of a different relationship like an exponential or something else, but still there might be another way of looking at whether or not this fits a linear function. And one way of checking whether there is linearity on the outcome is by using a quadratic term in your model. And to do that, the first thing that we'll need to do is actually make a quadratic term of the independent variable. So what we can do is we can go to transform, compute variable, and we call the new variable BMI2, and we have it be equal to BMI squared, just like so. We can paste that away and run that. And then what we'll do next is we'll go to analyze, we'll go back to regression like we did earlier, linear obviously, and the only thing we need to do really is make a new model with BMI included but also with BMI squared. We can paste that away as well and run it. And we'll get the same amount of output. There are just some differences, of course, because we're adding an extra term. And the thing that we're interested in this case is the square term in the regression model. And what we'll be looking at is whether or not the coefficient for BMI squared is statistically significant. In the case that it is significant, that indicates that a square term fits the model better than a straight line. And in that case, you may safely conclude that there is no linear relationship. In this case, the square term is not significant, indicating that a linear function fits the model better. And in that case, you can safely assume that there is indeed a linear relationship. There is also another way of looking at linearity by using dummy variables. So you can split up your dependent variable in groups and then judge by using dummy variables whether those dummy variables increase or decrease, for that matter, with the same amount of units for each step. But that is something that I'll go over in a different video when we'll be talking specifically about dummy regression analysis. Now, there is one last thing that I also wanted to touch upon, and that is homogeneity of variances, because we also used the scatter plot for that. But in this case, it seemed fairly evident that there was no deviation from homogeneity, but you can also check that using descriptive methods. One thing that you can do is you can actually look at the variances in blood pressure over different groups of body mass index. So what you can do is you can also go to transform, rank cases, then take body mass index and divide it into categories of the same sample size. So let's make 5 groups, for instance, using the rank case function. Paste and run. And then the next step would be to make a descriptive table, for instance with compare means, of systolic blood pressure divided by the different groups of BMI. Now make sure that you have your standard deviation on, because that's what we want to be looking at, the spread in each group. We can paste that and run it, of course. And what you'll be left with is a table that shows you for each group that you made for BMI the descriptive statistics of blood pressure. And we can see that the standard deviations, of course, are not the same, but they are also not very strongly different. And usually a rule of thumb could be that the biggest and the smallest standard deviation in groups cannot be twice as large. So that is it for the linear regression. This is, of course, the very basics, and there's a lot of other things you can do in SPSS when you are using linear regression. But these are the fundamental principles, and hopefully this video helped you to further your knowledge on that. In the next videos, we'll be looking at logistic regression, which is a way of analyzing dichotomized outcome variables, which is different from, of course, linear regression, where we were using continuous outcome variables.